Hello, welcome back everyone. Today we're going to be going over how you can use a flow cell apparatus to conduct fast scan cyclic voltammetry measurements, as well as how to set up the corresponding hardware and operate the software. As with many FSCV experiments, you're going to start with a potentiostat and its associated cords. This particular potentiostat has a BNC and a swivel/head stage input on one side, and we are going to use the BNC input today along with the cord that comes with the instrument. On the other side, we have inputs for the power cord and a USB cord to connect the instrument to your computer, plus an input that allows you to perform manual injections of sample indicated by the green arrow. Today, we will be performing automatic injections using another instrument that we will touch on shortly, so we will only use the USB and power inputs. And here we have an example of the potentiostat with the BNC head stage, the power cord, and the USB cord all connected to the box. Another vital aspect to FSCV data collection is a flow cell apparatus contained inside of a Faraday cage to ground the instruments and prevent excess electrical noise. So let's open up the cage and see some of the important components. Inside, we have a 6-port HPLC injection valve, a glass bubble trap, a manipulator and arm to hold the electrode in place, a basin with an inlet and outlet to allow for flowing buffer to reach the electrode surface, a ribbon to wick away excess moisture, and a waste jar under the basin with tubing feeding from the HPLC pump located outside of the Faraday cage, as well as grounding wires connected to the cage itself to prevent excess noise in the measurements. Now we are going to place the potentiostat inside the Faraday cage and connect it to a power source and a computer. As I mentioned previously, we have a 6-port HPLC injection valve inside the Faraday cage, and we also have a digital valve interface mounted to the side that allows for automatic injections of sample. To make the DVI compatible with the software we are using today, we will be connecting an external TTL instrument like the one shown here. We have a USB input on one side to connect a computer and a 12G 34G input similar to the potentiostat on the other side. You can be sure you are inserting the corresponding cord correctly by orienting the spines on the top to align with the hole. We have an example DVI here, and to connect the TTL instrument, you will want the colors on the cord to be oriented in the same way as the colors on the DVI itself. Once the TTL and the potentiostat are plugged in and connected to the computer, we can start preparing our running buffer. Here we are using phosphate buffered saline, but you will want to use anything that has a high ion concentration to allow current to flow. We will start by filling up the bubble trap about halfway with the same buffer, and then we will fill a syringe and place it into the HPLC pump, making sure to remove any bubbles. Today, we'll be running the buffer through the system at a rate of about 1 milliliter per minute. To get the buffer to fill the basin more quickly, we can hold the start button and purge the system. As I noted before, a ribbon leads to a waste jar under the basin to wick away moisture, and tubing leads from the basin through the injection valve and into the waste jar to allow the buffer around the electrode surface to cycle continuously. Now that the basin is filled, here is a close up of the arm that our electrode will be attached to. Looking closely, we can see two slight divots on each side, indicated by the green arrows. This is where you will slot your electrode in place when securing it to avoid breaking the glass. Because we are using glass insulated carbon fiber microelectrodes, be very careful with this step. Now, taking the BNC head stage that we attached to our potentiostat, take the red wire and attach it to the end of your electrode like shown. This wire is meant for your working electrode, while the other wire in black is meant for your reference electrode that we will place shortly. Today, we will be using a silver-silver chloride reference electrode. Here we have a piece of silver wire wrapped in heat shrink with a gold pin soldered to the end. To chloridize it, we first need to sand it down and then take a battery with a silver wire attached to the negative terminal. Using a grounding cable, connect the positive terminal of the battery to the gold pin of your reference electrode. Then put both the silver wires into a high chloride solution, such as sodium chloride or hydrochloric acid. You should see bubbles form on your reference electrode, and it should be white when removed from the solution. Now that our reference is chloridized, connect it to the head stage in the same manner as your working electrode, using the black wire this time, and then completely submerge the electrode in the buffer. Once your reference is plugged in and submerged, you can begin to lower your working electrode into the buffer. The basin should have a hole in the center like the one indicated by the green arrow. You will want to make sure your electrode is as centered in the hole as possible, or your measurements will be skewed. I recommend experimenting with the controls on your specific manipulator to become familiar with them, and know that we often adjust the placement of the electrode throughout the experiment to make sure the recordings are of sound quality. If you find it easier for you to lower your electrode and then connect it to the head stage, then feel free to go in whatever order is most comfortable. At this point, all of our hardware should be connected. We should have buffer flowing through the system, and our reference and working electrodes should be submerged. Now we're going to open and prepare the software that we will be using today to make these measurements. We will start by going to Setup Hardware in the top left corner, and we will click Connect and connect the TTL device first. For this purpose, we will leave all of these settings the same, and next we will connect the potentiostat. Now, in the top middle, we can turn on the display, which will reveal the live color plot being generated as our working electrode is sitting in buffer. Before we adjust the color plot, we can go to the Scope tab, which shows us current versus voltage index. If your electrode is in buffer and unbroken, it should look something like this while using a standard triangle potential waveform. We can also go to Setup Experiment in the top left to adjust electrical stimulation parameters under the Stem tab, or the potential waveform that is being applied over time under the CV Ramp tab. From here, you can change things like sweep frequency, starting potential, peak potential, and scan rate. The software is pre-programmed with the waveform optimized for dopamine detection, so we will leave everything the same. If you have the TTL device connected, then an option will appear to enable or disable automatic injections. Before recording, make sure you have a source of gas available to switch the injection valve, which will push the analyte through the sample loop. From here, you can change how long after pressing start the injection will occur and how long the valve will stay open. In the top right, you can choose to record multiple runs or a continuous run instead of a single file. You can also change the length of the file you are recording. For this purpose, we will change the length to 30 seconds. You can also adjust where the file will save, as well as what each file will be named as it's recorded. In this video, we will be performing a dopamine calibration of multiple concentrations with at least triplicate injections of each, so we will name everything accordingly. Now we will adjust our color plot, which has potential on the y-axis, time on the x-axis, and current on the z-axis in false color. To be able to see the currents generated from the oxidation or reduction of an analyte, we will need to enable background subtraction. From there, you can scale the colors based on your preference. We prefer to scale it with a maximum current of 10 nanoamps and a minimum of -5 nanoamps at first. And we are aiming for a smooth butter yellow that indicates our background is stable. The black spots appearing on the screen now are likely due to electrical noise, which is a good sign that you need to ground the instruments in the flow cell better. Anytime you would like to reset the colors, you can press Set Background. To manipulate the filter settings, you will open Setup Filters in the top left, and from there you can enable or disable the background or adjust the filters for the live display or for a file. Here I've opened an example dopamine injection to demonstrate this. You'll want to make sure the background remains enabled to be able to see any signal from your analyte. The software comes pre-programmed with several filters that are widely used for dopamine detection. Now that we have gone through how the software works, we are going to do an example dopamine injection. Here we have three concentrations of dopamine, 250 nanomolar, 500 nanomolar, and 1000 nanomolar, all in the same buffer running through the flow cell, as well as a 5 milliliter syringe. We are going to perform triplicate injections to analyze in the next video. As you prepare to inject your sample, make sure there are no air bubbles as they will interfere with the measurement. We will inject about 1 milliliter of the analyte solution and then start the measurement in the software. Please note that the measurement taken here is not of the same concentration as the sample injected in the previous clip. If the electrode is placed properly, you should see a distinct bolus of color rather than a smear, which indicates the electrode is not properly centered. Often it takes several attempts to achieve a good file. Whenever troubleshooting a problem in the flow cell apparatus, it is best practice to raise your electrode out of the buffer first so as not to break it, unless it's required that it stays submerged. Thank you so much for watching, and I hope you found this helpful. In the next video, we will go over how to export the data you have collected and how to create a simple calibration plot to extrapolate recorded current to concentrations.